So my name is Cotrina, and I am a hardware and a software developer. I have been working 8 years at this company, and what I do is I design and implement automotive secure gateways, and I focus in cybersecurity and in the communications inside the car. And okay, this is my job, but then when I don't work, I like to play with things around. One of the things that my company produces is a product that implements an intrusion detection system that operates at the layer 2 of a switch. Let me show you. This is the product that we have. I'm not going to sell it. So we have this ECU that is a ECU with networking. So it has a secure gateway. It can act as an update master. It can be a domain controller and does central and zonal computing. So these are the network capabilities. It has 6 100 base T1, so that means that acts over a Ethernet ports, and it acts as a gateway for Ethernet. But also it has one 1000 and one TS base TX, and this is what we use for OBD, to connect to the external world. We are the gateway, so we talk to the world. We are the guys that try to protect the system. We also have, the controller has 12 CAN, and the main purpose of this product is to do CAN to CAN in a gateway, CAN to Ethernet, so we encapsulate CAN into Ethernet and we encapsulate the other way around, and Ethernet to Ethernet, and also is the OBD port. So for this it has a Ethernet switch made by NXP, and this is the brand for it, so that you know it has like 2000 pages of documentation. One possibility that it has is that it has filtering capabilities on the MAC level. I will explain a bit of the architecture. So this is the switch, and the switch has some Ethernet controllers, so we connect to the domain controller for the BCM, the domain controller for the VCU, for the IDC, for PAM, for the TCU, and also connect to the OBD. Also, this connects to our microcontroller. So it is important to distinguish what is the switch that acts mainly on the network layer, transferring Ethernet packets, like the one that you can buy at home for routing. There is a microcontroller that can configure that, and also this is connected to a kind of a CAN switch. So it accepts several CAN buses, goes to this one, and from this bus it can filter and transfer packets to the next bus. So it's a CAN gateway, a Ethernet gateway, and following this one is a CAN to Ethernet. So as you can imagine, we want to have security here. So the Ethernet packets has a header, that is the MAC address, and there is a MAC address for the sender and MAC address for the receiver. The MAC address has 6 bytes, 6 offsets. The first 3 offsets, the first 3 bytes, they are defined by the manufacturer. So for example, if you buy one ECU that has Ethernet, not only an ECU, like any Ethernet connector or this USB to Ethernet, it will have these first 3 bytes defined by the manufacturer. For example, Continental in the Czech Republic, they can give only these first 3 bytes. So if you ever see an ECU that sends Ethernet packets having these 3 bytes at the beginning, you know that it has been manufactured by Continental. For example, our company, we manufacture ECUs, and we have been given these 3 offsets. So every packet that comes from this side, it comes from our ECU, so it has to have these 3 bytes as the sender. If another ECU wants to talk to us, it needs to send the address to this one, and then the other 3 bytes for our ECU. So I will explain that in our switch. Let me start from the bottom down. So the port 6 port 6, that is the BCM, it has this MAC address. Every packet that wants to arrive at this one needs to have this as a destination. Every packet that comes from here, every Ethernet packet, needs to come from this one. And this, the manufacturer, the OEM, told us the BCM will have this MAC address. So you have to know that. Good. Same thing for the VCU. It has this address, so we know from the time that we produce our ECU. Similar to the IDC, is fixed at manufacturing time. So it might be, okay, let's go to the PAM. The PAM is manufactured by D0B498, so it's by Robert Bosch, for example, and we know that it will have these 3 bytes because it's manufactured by Bosch, and the next 3 bytes, they are variable at manufacturing time. So in one vehicle, you might have a PAM ECU having these 3 bytes, and then 01, 01, 01. Another ECU will have 01, 01, 02, and whatever the manufacturer for the PAM has defined. Similar to the TCU will have the first 3 bytes, in this case E413, so we know that it's made by Continental, and then it will have these 3 bytes. The SDW, this is us, so it has the first 3 bytes made by TTTech, and then these other numbers is for every ECU that we manufacture, so we know that. A different problem is for the OBD. The OBD is a tester that can be a PC in one workshop, it can be a PC in my desktop, so we don't know which MAC address it will have. Every network card will have a different one. So we have a bunch of different ports where different ECUs will talk, each of them will have a MAC address. Usually this is resolved with IRP. So you have someone that arbitrates which which MACs belong to which port. And this is also known as the AL2 lookup table. So we can configure and tell from this input port, from port 6 for example, it has to have this source MAC. So that means that only the BCM can talk on the port 6, which makes sense because we expect that the BCM with the given MAC address is in port 6. And then we can say from this port you can talk to this other, from this MAC you can talk to these other MACs. For example, if the BCM wants to talk to the VCU, if we want to allow that, we say from entering port 6, using this source MAC address, you can go to this target MAC address and we will send it through this port. So we will not send that packet through this port because our routing table doesn't allow that. So the problem is that, as I explained before, the system doesn't know some MAC addresses because we don't know this one. It can be, we know the first 3 bytes, but the second 3 bytes depend on ECU to ECU. So we cannot make this filter at the very beginning when we deliver the ECU. How do we solve that? So starting from the bottom, for the BCM is easy. We know which MAC address it has. For the VCU, we also know that. For this one, we also know. For the PAM is variable at manufacturing time. So that means that there can be only one we don't know, but once that we know, we can remember it. And this is what we do. We wait for the first message that happens at the end of line, not when the car is running, but the end of line when they do the vehicle testing. And then what we do is we learn the second part, the PPP, and we remember that. That means that we can configure the table. For the TCU, the problem is that it's variable at runtime. You might have one TCU in one run cycle, but maybe later on the TCU acquires a different MAC address. We don't know why, we don't know how is the requirement. And then what we do is we wait for the first message on its power cycle, and then we learn TTT. That means that if another message comes from this port, it needs to have the MAC that we have learned. Okay, so for the SDW, our switch, we know the MAC, and for the OBD, any MAC is allowed. So we have some rules to find which MACs we can use. So now, what we want is to set up this so that, again, only packets from the BCM arrive at the BCU. If the IDC sends packets, we don't want to send to this port. So how do we test that? So we have a PC that sends packets. This PC maybe has an Ethernet port, maybe it hasn't. So what we do is we connect to this converter, converts to Ethernet, and the Ethernet we convert to this media converter because our ECU talks 100 base T1. So we don't talk pure Ethernet, we talk T1. So we convert into this T1 with these broad and rich cables, and then it goes into our connectors, into the switch. Now let's suppose we want to emulate another ECU. So we send it through the broad and rich cable, category 5, and then we can connect to the Hydra link that you can buy outside. I'm not affiliated with them, and then it goes to the PC. So this is our test hardware. And this is the point of the conference. We use Scapy to send packets. So for this, there is an API that is called sendp that operates on the L2 layer. And this allows us to select a Ethernet packet where we select what is the source address, even though Scapy doesn't seem to matter, doesn't care what is the source address, the destination address, the IP, and then some data, just because we want to send some known packet. So that is easy. This is how we send one packet coming from this one, I think this is the BCM, arriving to the TCU, for example. And this is just for one packet. So what we want to do is for each source MAC, all of this, for each destination MAC, the other ones, for each port, we start sending packets. So what we do is a matrix of 6 ports by 6 senders by 5 receivers. So we have all these packets and we build them, and this is what we get. So we have a good packet. So we using the sendp API in the Ethernet layer L2, we send from the BCU, that is this address. So you see here when we send the packet, this is the sender address to the destination. So we specify also here, we complete the packet to have something, and we introduce a payload. So when we send, and we send from the BCU port. So again, this one will send this packet, and you see it here, and you see it here, that is this one, will send to this one, that is the BCM, and we see in Wireshark that it arrives. Good. We send a packet from one port and it arrives at another port. That is how it is supposed to work. But the point now is that we have this thing. Maybe some packets we forbid them because they are not supposed to go around. So this is a packet that we are simulating to see if our firewall is working. We send a packet that is sent from the VCU, but is not using the VCU MAC. Is simulating, is pretending that it comes from the SDW. So we have a packet coming from one ECU, pretending to be this one, and then let's see if it arrives here. So the same thing, we send from one source address, simulating this, pretending that we send to this destination through this interface. and then this is bad because the packet has arrived. So this is a sample where the firewall in our switch didn't work. The packet has passed. But we need that because we need to know that our firewall works or doesn't work. On this one, we found an ugly case is that we sent 3 packets, but only one arrived. We were very confused about that. Like, we waited a bit of time, like 1 second between one packet and another, and then we got 3. Okay, maybe Scapy is not fast enough, maybe it doesn't see this one, but we see that they are sent. We tried with a C program, and we saw that also it was working. We tried with another Windows, we tried with another Linux. Okay, we thought that maybe the adapter, the Ethernet plug, was caching the packets, saying, oh, this packet is the same as this one, that is the same as this one, so I will just send one and save you traffic. Okay, maybe the problem is that the traffic was not sent. Maybe the firewall that we implemented was too slow, was eating the packets and not sending them. So we gather statistics to see how many it sent. Maybe the problem was that Wireshark was not seeing the packet, so we captured with Scapy. And then at the end of the day, what happened is that the adapter that we were using was wrong. The packet was arriving, was going through the firewall, everything was passing, and when it was arriving at this other side or this other side, just it was lost here. So it's a mystery, we don't know why it happened, but okay, glad that we have a workaround for that. So this is how the normal scenario works. And now we are going to go one step beyond. So the first firewall that I show is only on the MAC level. Source addresses, target addresses, ports. Does anyone recognize this one? No, I am too old for that. Okay, thank you very much. So what we do is that this switch supports deep packet inspection. So inside the switch, you can also select further rules, not only in the MAC level, but also in the packet level. For example, we say, oh, this packet that comes from this MAC, in the Ethernet packets, the destination is the first 6 bytes, not the source. It's a bit strange. So the destination MAC goes first, and we say, if it comes from this destination MAC, it is good. If it goes to this one, to any target MAC, then it is good. If the packet is of type 0800, that means an Ethernet type, then it is good. If the protocol is 11, so if it is a UDP packet, then it is good. If it comes from this IP address, then it is good. Otherwise, we don't like this packet. So this is not only on the layer 2, not only on the MAC, but also investigating a bit into the Ethernet frame. So this is what we did. We set up scenarios for that. And we went even one step further. And this is where it really joins to the automotive world. What we did is we encapsulated a UDS inside DIP, inside TCP, inside IP, inside Ethernet. So there is a feature of the switch that allows to set up filters further levels. So you can set up filters on the TCP header or in the packet level. So this is what we did. We said same thing, basic filtering on the destination MAC, on the source MAC, on the protocol 6, whatever it is, on the source address, on the IP addresses. And then we set up a filter on the DIP. So 02 is the DIP protocol, FD is the inverse of that. That is how you send a DIP packet. You send 02, that is the version of the IP, and FD, that is the inverse, and then the diagnostic. 8001 is to send some UDS, the length of the packet, and then here is the source address. Again, this is DOIP protocol level. Source address, target address, and then the service. If you remember from previous talks, and I am glad to give the talk now that I have explained the other things, there are different UDS with different types. So 22 means to read. We have seen in other talks that 2E means to write, or 11 means reset, or 10 means session, different types. So using our firewall, we set up DOIP rules. So this one is a message to read 22, the DID 1004, that happens to be the battery voltage. So this is how we did. We sent using Scapy, using this API on the UDS level, using a DID with identifier 1004, that is a battery voltage. We send it and we receive that. Good, the firewall has this rule and has allowed that. Also, we try to send a packet using the 1005, and it also got a reply, a negative reply, but a reply. So that means that the ECU on the other side managed to reply to that. So that means that we have allowed this packet, and that is bad, because our firewall says that only this packet can flow. So this is a bug in our firewall rules. And then we send a packet with the 1006, and using this Scapy API, using this identifier, and it never got a reply. In fact, we saw that it never arrived at the other side. Why? Because the firewall has truncated that, has dropped the packet. So, yeah, not only it didn't reply the other ECU, but using the capabilities of the switch, this has been logged. We know that someone has sent a diagnostic that we, as the firewall, didn't allow. In a similar way, here, when we send this packet, we should have received an alert because of that. A packet that should not have arrived. If we had blocked it, we will get an alert in our IDS. So, yep, this is how we use Scapy to send diagnostics. So, if the ECU, the final ICU, likes this DID or not, it's not our problem. We just act as a layer 2 firewall. We prevent the packet from arriving at the other side. So all these attacks that says, oh, we can send the 2E message to read the memory. Sorry, we don't allow that. We send this diagnostic session to attack the other ECU. Sorry, our gateway blocks that. So that looks very easy. Just send this packet, it arrives or it doesn't arrive. Yeah, that is for one packet. Then it comes the heavy task, because there are many messages, there are many services. 2 read by identifier is very easy, but there is 2E to write by identifier, or there is the 31, a routine, as they have commented before, of the 11 to do a reset. So there are many messages that not only we have to try, but also we have to configure in our rules. So here, when you see 22.1004, we have to define rules for all the DIDs that we wanted. We have to define rules for all the services that we wanted. So in the same way as there is a 22, there is also a 11 if we allow it or not. So that took some time to create all of that. Then for every service, it might have sub-services. So 22 is read, so how many identifiers you can read. Routine is only 31, but there can be 100 possible routines. So yeah, multiply this by 200 items or 10 items. Then we had to add this test to a testable tool. So it's okay to define in Scapy using a Python script, but then this is not really usable by our client, by our OEM. They say, we don't understand this. We don't want to install Scapy, even if they can just download as an executable, as Philip mentioned before. They don't want that. This is a company. They don't like to play with things that they don't know. So they wanted something that they know. For example, Canberra Studio Diagnostics description or ODX. Not only that, we also had to map each of the sessions. Then every of these messages, for example, the routine, they might have different lengths. When you erase something, then you have to specify parameters. Or, for example, the memory might have an address and a length. So do we want to filter only by the erase message, or do we want also to say, oh, you can erase only this range? So again, if the final ECU doesn't want to protect addresses, we can do it on the firewall. And this is kind of useful when you have a legacy ECU that you cannot even change. As an OEM, you cannot change, but you can install a firewall in the middle that will protect from that. And that means that as the firewall is kind of a modern ECU, we can update these rules. Your ECU can remain vulnerable from the inside, but not from the outside, because everything that passes through the firewall, for example, from the OBD, we are going to protect it. So we are kind of the good guys for the OEMs, the bad guys for the hackers. So, and with this, each service can have parameters. For example, the link control supports also baud rate identifier and baud rate high byte. And that is something that Scapy, thanks to the UDS protocols by Dr. Niels, it supports that. He has implemented all the UDS messages, so we can play not only sending the 87, but also with different baud rate identifiers and different baud rate high bytes. So we converted that into that's one of these files. He created one for BMW and another for Volkswagen, but not for Mercedes. So we created one because we have the diagnostics for the customer, we can do that. Unfortunately, we cannot share that, NDA and all this stuff. So we created several, well, a lot of cases, like 300 allowed cases that pass through the firewall, and 4,000 that, oh, no, you cannot write this identifier. You can write this one, but not this other one. So we created a lot of pass cases and a lot of fail or block cases. With that, we also try to be creative. For example, for the write data by identifier, someone explained before that after that you say what is the identifier that you want to write. I want to write the VIN. So 2E, 10, whatever is the VIN, and then the VIN data. Look, that is easy. But for the 22, I was surprised to learn that in the 22, you can read more than one identifier. You can say 2211, and that will read the DID 11, but you can also say 221122, and it will read two identifiers in the same message. So, yeah, some of these services allow only one sub-service, but some of them, in particular the 22, allows more than one. So we have to be creative for that. Again, thanks to the implementation, the UDS to read data by identifier, you can specify two of them and it will send both in the same packet. It will not send two packets, one to read one, another to read the other, but it will send in one packet. And that broke our firewall because you say, oh, we can read the 221004, but we don't have a space to say another DID. So we allow or we forbid the first DID, but for the second one, we decided, sorry, we cannot deal with that. We don't have a space for that firewall rule. So we are not allowing that. Even if the specifications that you can send more than one DID is our limitation in our system. Another thing that we have to be creative is that some of the services, for example, 3E is the tester present, and it allows this suppress positive response. It has been explained also before. So it's not only 3E00, it's also 3E80. So in our firewall, also we have to open the 3E80. And one thing that you need to fix is that the service 11 also supports the suppress positive response. So yeah, 11, that is diagnostic session control. If you remember from another talk, session control can be 01 for default, 02 for programming, 03 for extended session. 03 is for extended session. 83 is also for extended session, suppressing the positive response. So, yep, tricky one. So one other thing that we found is that the VIP 13400, the 2019 uses the protocol 03. So here I said that the VIP message starts with 02 FD. No, the 2019 DOIP starts with 02. The 2012 starts with 02. The 2019 starts with 03, and then the inverse is FC. But this we could also change in the Scapy Automotive. So we also had to be creative. For example, the payload length can be 0. So it was a bit tricky to send messages with 0 bytes, but okay, we found a workaround for that. And we need to send a huge message. When we try to send a message with 4 gigabytes, it crashes. Like the computer says, or the Python says, sorry, I cannot allocate all these bytes to send through Scapy. So it's not a Scapy problem, it's a Python problem. Or maybe I need a powerful computer. One other thing is that the length can be variable. As I said, some messages, they support a variable number of bytes. Are you out of time or something? Okay. So we got some ideas from this scanner and from this one. So again, thank you very much for creating this one. We copied and pasted. We are using the 29 authentication. William said that many people are still using the 27, not us. We are using Ethernet, so we are in the future already. And it's good because Scapy Automotive supports the authentication with certificates. We have to be very creative here because how do you create certificates for that? So the certificates is a payload, but you cannot just invent it. It needs to be an authentic certificate. It needs to be properly signed, and this is where we found Alex implementation that said, oh, I have some messages, but I cannot share them. Same thing for us. I can create a certificate used for the 29, but I cannot tell you. I have to kill you afterwards. So some other things that this is implemented after the TCP header, so we have to think about that. Other things, you can do TCP fragmentation, so you can send a packet that includes only half of it. So you can send only these bytes, and then the next bytes in the next packet, because this is a TCP connection. Nobody stops you from sending the minimum size. So we have to simulate that, splitting that in 2 packets in Scapy, but we could do that. We have to whitelist other packets, and one important thing is that there are many other messages. It's not only diagnostic. You have ARP, you have sync, you have vehicle annonces. All of that needs to pass through the firewall. And that was the painful realization. Like, yeah, the firewall works, but everything else is broken. So we had to fix that. And one thing that we didn't know, and I found today, is that how to integrate the tests and the results with our tools, because we are a tier 1. We cannot just make the scripts in Python and release into a repository. The customer wants to see that. We need to integrate into our V tool, as, sorry, I forgot your name, as Thomas explained before. Like, we need to document that. It needs to be tested, system testing, unit design, blah, 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 and that. So doing this is the easy part. Doing this is painful, but doing this is boring. So we also had to deal with the IT. They didn't want us to install the tool. They didn't want us to open this port. They didn't want us to connect USB dongles. So if you are in an enterprise, in a big company, be careful with that. So you are in the middle of that, but there is other people that want to create problems for you. The same problems that you are creating for the hackers. So, yeah. So other alternatives that I'm not going to mention. So the conclusion, yes, we are using Scapy to test our firewall. Is very viable, and we need to thank Philippe and Dr. Niels, because we are standing on the shoulders of giants that have made our work easier. So thank you very much.
Thank you. Thank you very much for the talk. Any questions from the audience? Okay, let's start here.
Thanks, very nice talk. So when you're talking about deep packet inspection, have you considered using a deep learning approach or AI?
No. We consider and we rejected that. First, because we want to be, how is called that, the same thing happens again and again. Not reliable, but deterministic, exactly. So using AI or machine learning or expert systems, you don't know what is going on.
Yeah, because there's a lot of research right now, and also I think it's not really a viable solution with the false positives you get.
Yeah, yeah, and also we have to analyze all of that like too much, and also consider we cannot give our ECU, we cannot give this intellectual property to researchers. So it's like, yeah, you can implement the algorithms, but you're never going to test in our ECU.
Thanks.
Thank you.
Thank you for the presentation. My question is, what is preventing in the gateway to be vulnerable to replay attacks? Because, for instance, what about the scenario that an attacker gets access to the OBD port, right? And with some previous successful communication that was sniffed, then could spoof all that parameters like the MAC address in the packet and request, for instance, if it's allowed security, the UDS service 22?
Yeah, I knew I was getting that question. So one thing that we do is time, what's called, TSN, time sensitive network. So that means that we know when, from the OBDs it's different, but from the other ECUs, we know when they are supposed to send Ethernet or CAN messages. So if they are out of time, we reject them. That is, you can do with time-sensitive network or with allocating frames, like time frames for every ECU inside the switch. For the OBD is different because it's a PC2, you cannot control that. But for this, we rely on higher protocols. For example, authentication. So we use the 29 service because that has a certificate. I mean, if someone manages to fake a certificate from the vendor, it's a bigger problem. You don't fix that with an Ethernet switch. You fix that going to the OEM and telling him, what are you doing?
That's the target. Ask question.
Yeah, hi. Yeah, a gateway solution is really good. Thanks for that. But in your talk, you mentioned about the legacy ECUs can be protected through this gateway, right? But always hackers is always wants to go for the legacy ECU, so try to modify the payload or the firmware. But again, the gateway will passes the payload, whatever it is given from the legacy ECUs as part of the normal way of working.
You mean a packet coming from another ECU or from the OBD port?
No. The legacy ECU, for example, I have a gateway, I have a legacy ECU, but I am trying to physically manipulate the CAN, okay, from the vehicle, and I'm trying to alter my firmware itself. Okay, but still the understanding between the gateway and the legacy ECU is the same. Okay, so this case probably we may be functionality wise we may be altering it, but not as part of the framework wise. What I feel is, so then there will be a bigger problem, even though we have a gateway and everything is working fine. But if we are able to do this way, then there will be still we are the vehicle is under the hackers' control.
Okay, you are right in that. First, because this is a Ethernet gateway. For CAN, we don't use this method. For CAN, we have this LLC that can do this thing. So it can filter messages, for example, through time. This CAN message is not supposed to come twice in a second because it has a periodicity of 1 second. Why is coming another time? We can also react to that, like, why are you sending so many authentication? We can just cut the port. I mean, we are in the middle, we are the gateway. So we can say, some ECU here is misbehaving, I am going to drop the CAN here. Or I am going to switch off the car. I am going to tell the battery to go off, go into limp mode. Because for good or for bad, we are the higher policemen here. So we make the rules. If someone doesn't comply, we decide what to do about that. So with time is important. And also we can filter on here on the CAN itself. So we can, in the similar way, this is more for CAN, so it doesn't apply to these kind of messages. So in the same way as here, we can define a range. This signal, because the signal is part of the PDU, this signal needs to go between 0 and 240. I think some presentation said, oh, if it goes over this limit, then you are vulnerable. Well, we can filter that also because we have a PDU IDS. But I didn't want to talk about that because we cannot simulate that in Scapy, because it's very CAN related.